So I was cleaning out my fridge last weekend, and way in the back, behind a jar of pickles I definitely should have thrown out years ago.
Oh, no.
Yeah, I found this old Tupperware container, and I honestly couldn't tell you what was originally inside because it had been completely taken over by this fuzzy green civilization.
Yikes.
Right. I was about to toss it, but I stopped and thought, this mold is persistent.
It really is.
It's thriving in the cold, dark corners of my kitchen. What if that fuzzy nuisance was actually a high-tech miner capable of surviving where our best machines fail?
That is a surprisingly relevant kitchen nightmare.
Is it?
Because while you were staring down fridge fungi, scientists were actually sending a distant cousin of that mold to the International Space Station.
Wow, really?
Yeah, to see if it could unlock the resources of the universe.
And that is exactly the theme of today's deep dive.
Whoa.
We are getting intellectually curious today about the BioAsteroid experiment.
Right.
We're looking at how a humble fungus might be the key to mining rare metals from meteorites in microgravity.
It really makes you rethink who or what the best agent for a job actually is.
Speaking of finding the right agents, that's exactly what our partner EmberSilk does for digital workflows.
Absolutely.
If you're looking to uncover where AI agents can make the most impact for your business, whether it's training or automation or integration, you have to check out embersilk.com.
They definitely help you build the right solution for your AI needs.
For sure. But back to BioAsteroid. In this case, the job was mining rock in orbit.
Exactly. So let's set the scene. We aren't in a mine shaft down here on Earth.
Right. We're aboard the ISS.
Inside the K-Ubique incubator, the researchers took these tiny fragments of an elchondrite meteorite.
Stony rock from Northwest Africa. Right?
Yeah. And they just let them float there for 19 days.
Now, I know space complicates basic physics, but why does it make chemistry so difficult?
It comes down to the lack of convection.
Okay.
On Earth, gravity drives fluid movement. It mixes chemicals naturally. But in microgravity, that stops.
So everything just kind of sits there.
Right, you get this stagnant boundary layer right around the rock. If you just rely on standard chemical leaching, the fluids don't cycle.
The reaction just hits a wall.
Exactly. In this experiment, the abiotic extraction, so the non-biological extraction of palladium, it actually dropped by a massive 13.6-fold compared to Earth.
Wow. So the chemistry essentially suffocated itself.
It did. But then enters Penicillium simplicissimum.
A filamentous fungus.
Yes, a filamentous fungus. And you might wonder how it handled that stagnant environment.
I am wondering exactly that.
Well, it handled it remarkably well. The theory is that the stress of the microgravity environment triggered a metabolic shift.
Like an oxidative stress response.
Precisely. As a defense mechanism, the fungus actually started overproducing carboxylic acids.
Wait, so the biology didn't just survive the lack of gravity, it used the stress to become a better miner.
It sensed the hostile environment and got aggressive. The fungus increased the extraction of palladium by 5.5 times compared to the sterile control.
That is wild. It completely outperformed the laws of chemistry by adapting its own metabolism.
It's incredible adaptability.
But I read they also tested a bacterium, too. Sphingomonas dissecabilis. Did it have a similar reaction?
Actually, no. The bacteria illustrated exactly why you have to pick your biological agents carefully.
Oh, really?
Yeah, instead of leaching the metal, the bacteria formed a biofilm, basically a slime layer over the rock.
Oh, so it created a shield.
Exactly. It created a mechanical barrier that completely blocked the extraction of palladium.
So while the fungus was drilling in, the bacteria was sealing it off.
Showing that not all microbes are natural-born miners.
Let's talk about the target here, though. Why palladium specifically? I know it's rare, but what makes it the priority target for a space colony?
It comes down to utility. Palladium is known as a hydrogen sponge.
Meaning it absorbs a lot of hydrogen.
It can absorb 900 times its own volume in hydrogen.
That is insane.
It makes it a master catalyst for fuel cells and life support systems. If you want to breathe clean air or generate power in deep space efficiently, palladium is your best friend.
But, and I love this detail, we aren't doing this to ship the metal back to Earth, right?
No, not at all. The yield on this experiment was tiny in dollar terms. Maybe $10 worth.
Right. The economics just don't work for importing it back here.
This is entirely about in-situ resource utilization, or ISRU.
Got it.
It proves that a future colony on Mars or the Moon could be totally self-sufficient. Instead of shipping heavy catalysts all the way from Earth,
You just grow a vat of fungus.
yes, you harvest what you need directly from the rocks beneath your feet.
It's the ultimate circular economy. You aren't just surviving in space, You're growing your own factories.
It really shifts the entire paradigm from mere exploration to actual habitation. It's such a huge, optimistic step toward making human life multiplanetary and completely sustainable.
That is such a cool perspective shift. Okay, I want to leave you all with a thought to chew on. If a humble fungus can intuitively outsmart the physics of microgravity to harvest resources, what other biological partners are we overlooking?
It's a great question.
What else is hiding in nature's library that could hold the keys to our expansion into the stars?
Nature has had billions of years of R&D, and we're really just starting to read the manual.
If you enjoyed this podcast, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.